Hi, this is Kevin from the Mathsaurus, and in this video I'm going to do question 1 of the Step 2 paper from 2019. And if you're watching this in 2020, Step 2 is one of the only exams, along with Step 3, that hasn't been cancelled, so I thought I'd put this out for those of you preparing for that at the moment. This is kind of an interesting step question. Question 1 here, it's a bit of an algebraic sort of exercise really, and this is often tested in step questions. Really, can you just churn through a lot of algebra? So actually, really it's a question about finding tangents, but to these general curves, and so it's testing, can you just apply all those results efficiently and quickly, and also your thoroughness in writing out the answers. In particular, paying attention to things like when it asks for an if and only if statement, making sure you really have justified carefully that your argument applies in both directions. So I hope it's useful for you. I've got quite a lot of other step video solutions if you check out my website, mostly from step 1, but 1 or 2 from the other papers as well. So let me know what you think in the comments below, and I'll try and put out a few of these before the real exams this year. So the first part of the question gives us a function f of x, which is x minus p multiplied by another polynomial g, and we want to show the tangent to the curve at x equals a passes through this point p0 if and only if g prime of a is 0. So looks like we've got a fairly algebraic question here, and we just have to try and follow our instincts and try to do the algebra as efficiently as possible. So we're talking about the tangent to the curve where x equals a, so I'm going to try and write that down as a first step. And so if we differentiate f by the product rule here, I'll just get x minus p times g prime of x, and then plus 1 times g of x. Okay, so this means then that, well, the tangent to the curve at x equals a is going to have gradient f primed of a, which is a minus p times g primed of a plus g of a, and of course it also passes through the point a f of a. Okay, so that means that its equation is, just using the form y minus y1 is m times x minus x1, is just y minus f of a equals a minus p g prime of a plus g of a times x minus a. Okay, just the ordinary form of a straight line here. Okay, now so we've got to prove this if and only if statement, and it's very important in step questions when you ask for if and only if you make it clear that your argument goes both ways. And it would be possible to write this down with each step going in both directions, but to be super thorough here, I'm just going to write it out in both ways, right? So let's start by saying, now let's suppose that g prime of a is 0. Okay, so and then let's also put in the x coordinate p here and see what the y coordinate is, right? So I'd get y minus okay, let's just plug it all in to begin with. Y minus f of a equals, now if g prime is 0, this term drops away, so I'm just going to have g of a times p minus a. And at this point we can remember that f is defined as x minus p times g of x, so this is going to be a minus p times g of a, so that's g of a times p minus a here. So actually I've got minus this, so actually these two terms clearly cancel out, right? A minus p is minus p minus a, so that gives y equals 0. Okay, so that means that the tangent does pass through the point P0. right? And so, you know, and then conversely, if the tangent passes through P0, trying to write these up in a sort of step-like way here, if it passes through P0, then going back to this definition, I would just put in 0 for the y coordinate, and then P for the x coordinate, so I would get something like this. Right, so, and again, we can replace the f of a here with the a minus p times g of a, so that would be, and then again you see, so it's minus in front of here as well, so again this term is going to cancel out with this one ultimately, but let's just write this all out. So I'll get a minus p times g prime of a times p minus a, and plus g of a times p minus a, so actually those two terms cancel out here, and so I get 0 equals, well let's write this as minus a minus p squared times g primed of a, and again in step questions you've got to be very thorough about all of the assumptions and things here, so I can divide through by a minus p squared here because a is not equal to p, right? Okay, so I'd say hence, since a is not equal to p, then g primed of a is equal to 0, and we've proved the if and only if really clearly in both directions. As I say, you could actually write this down with every statement if and only if you thought about a careful way of writing it, but this is thorough and clear that we've got the marks there. Right, so now we've got a curve that is in this cubic form where we can see the roots. P, Q and R are constants with P less than Q is less than R and A is a non-zero constant. Okay, so now the tangent to C at the point with x equals A, not equal to P, again passes through P0, so that 2A equals Q plus R, and find an expression for the gradient of this tangent in terms of A, Q and R. Right, so so again, clearly we want to write down an expression for the tangent here. And so that involves differentiating this function. So you've got a product rule with 3 functions. Now you can just do, this is 1 times the other 2 and then apply the product rule to those. If you're doing step, this might come up often enough just to kind of think about what the product rule for 3 functions is. So let's just think about that as an aside, right? So let's say I've got f of x times g of x times h of x, and I want to differentiate that. Well, by the ordinary product rule, let's think of it as f of x then multiplied by this function g of x times h of x. Okay, so I would get f of x times the derivative of g of x times h of x, and then I'd get f primed of x times g of x h of x. I don't need to do any more work on this function. Just apply the product rule again here, and we get f of x times g of x h primed of x plus f of x times g primed of x h of x plus f primed of x g of x h of x then. And you see that this generalized product rule for 3 functions just says, okay, it's kind of easy to remember once you've seen it once. It's the 3 products here, and in each of them, this one you've got f differentiated, this one g differentiated, and this one h differentiated. Okay, right. So let's take that little bit of theory, and as I say, you could have just applied this idea directly to the function, of course, as well. Okay, so if I have got y here, then dy by dx by this result. This does make it nice and easy to write down. Now I've just got I'm going to do a multiplied by, now actually if the 3 functions here f, g and h, all their derivatives are 1, so this is kind of nice. So if we differentiate the first one and leave the other 2 alone, we just get x minus q times x minus r. Differentiate the second and leave the other 2 alone, we get x minus p times x minus r. and then same with the third one, so we get x minus p times x minus q. Right, so again, right, we can say the tangent that we're looking for has this gradient then, again we're looking at the point x equals a, so it's going to have gradient a times a minus q times a minus r plus a minus p times a minus r plus a minus p times a minus q, right? And it's going to pass through the point A, and the y coordinate is a times a minus p times a minus q times a minus r, right? So we've got, slightly, nastier algebra here, but this is a common theme in STEP, where we just have to really try and keep going with this sort of stuff, right? So its equation is, again, I'll just write down y minus y1 here is equal to the gradient, which is now this expression that we've just written down, times x minus x1, so that's x minus a, right? Now, this time, we just have to show that if it passes through p0, then this equation is true, right? So if it passes through p comma 0, then that means that when I put in y is 0 and x equals p, I'm going to get an equation for these constants, right? And I'm going to hope that I can find a way of simplifying it. Right now, in practice, in a STEP question, you might, I'm doing a bit of duplication of writing things out here to try and be super clear. You may just jump to this line if you want to here, right? So then I substitute in x equals p, and we get this, and now we just have to look carefully at what we've got. Okay, so the 0 I don't need to think about here. What else can I cancel out? I've got the a's that are going to cancel out here. I've got p minus a and a minus and minus a minus p, so let's get rid of those. And then right, actually these brackets are no longer relevant, right? And now I've got a minus q, a minus r here, and also a minus q, a minus r here. So actually they're also going to cancel out. So this has worked out quite nicely, right? I just get 0 equals a minus p, a minus r, plus a minus p times a minus q. And now again, I can divide through by the a minus p here as well, right? So again, and this is because we're told in the question a is not equal to p, so I get 0 equals a minus r plus a minus q. Right, this happens a lot in STEP questions. Things, if you've got it right, things really simplify down nicely, okay? And this is exactly the expression that we were looking for, which is that 2a equals q plus r as required, okay? Right, now the question also says, and find an expression for the gradient of this tangent in terms of a, q, and r. You've got to be really careful in these STEP questions that you answer every part that you're asked to very clearly, okay? Right, so let's say that then. Further, well, the gradient, right, we already had an expression that we wrote down for the gradient, so it's a times a minus q, a minus r, plus a minus p, a minus r, plus a minus p, a minus q. And now this is an expression for the gradient, but we're asked to get it in terms of a, q, and r, right? So we need to only have the variables or the constants a, q, and r in here, right? So obviously I can use this thing that I've written down before to somehow get rid of the p that would be here, right? And if you look at this carefully, right, if I leave this first term alone and factorize out the a minus p here, right, so I get a minus p, and then this would be 2a minus q plus r, right, and by the previous thing we've written here, that would be 0, okay? So actually, this is just a multiplied by a minus q times a minus r. Now, a is also not one of the variables we're allowed to, one of the constants we're allowed to have in the formula, so I need to also replace the a here with q plus r over 2. Okay, so this is a times q plus r over 2 minus q times q plus r over 2 minus r, and then, okay, so this is q over 2 minus q, so that's minus q over 2, right? So this is actually a times r minus q over 2, and similarly for this one, r over 2 minus r gives me minus r over 2, so this is q minus r over 2. So I actually get here a over 4 times this difference of two squares expression. So if I pull a minus out of it as well, I can just write that as minus a over 4 times, sorry, not a difference of two squares expression, sorry, it's an exact square, so it's, if I pull a minus out, it's q minus r squared here, right? So so minus a over 4 times q minus r all squared. Okay, so the last part of the question here reads a bit like the previous part, right? It says the tangent to c at the point with x equals c, where c is not equal to r, passes through the point r0. Then we want to show this tangent is parallel to the tangent in part 1 if and only if the tangent to c at the point with x equals q does not meet the curve again, right? So so really, you know, we've got to notice that we don't need to do all the work again from the previous part. We can just copy it exactly, right? They've just replaced the letters here, right? It was x equals a here, and it's x equals c here, and it was p0 here, and it's r0 here. Otherwise it's the same, right? Okay, so we can just say, you know, repeating the argument from part 1, we're going to know that immediately 2c equals p plus q, right? That's just exactly the equivalent statement of 2a equals q plus r, right? And further, the gradient of the tangent here is just going to be minus a over 4 times p minus q squared, right? Okay, so the tangents are parallel then if the gradients are the same, right? So I'd have to have minus a over 4 q minus r squared from the first part of the question is equal to minus a over 4 p minus q squared from the second part of the question, right? So I can ignore the minus a over 4 here, obviously, and so I'd have to have either q minus r equals p minus q, or q minus r equals q minus p, right? But this case we don't actually want to think about because this would mean r equals p, and we're told in the question that that r is not equal to p, right? So we have this case instead, q minus r equals p minus, or we could say 2q equals p plus r, or something like that. Anyway, right, so this question then asks about the tangent to c at the point with x equals q. So that's the last tangent we need to think about, right? So let's say now the tangent to the curve at x equals q, that's going to have gradient a multiplied by q minus p and q minus r. Okay, right, and this is just using the result that we have for the gradient here, right? If I put in q to this, oh, I missed a square bracket there, then you know, this term is 0, this term is 0, and I'm just left with this one. So a times x minus p times x minus r with x equals q, right? Okay, so right, so it's that, and it passes through. What point does it pass through? Well, it passes through a point with x coordinate q, and the y coordinate is 0. Just again from the initial form of the function here, if I put in x equals q, it's a 0. Right, so okay, so its equation is just going to be, again, y minus y1 is x minus x1, m times x minus x1, so y minus 0 is equal to a times q minus p times q minus r times x minus x1, but the x1 here is q, so that's x minus q, right? So actually this is just the equation of that tangent, right? So we want to know whether this intersects the curve again, right? So this intersects the curve again, where, okay, this equation of the tangent then is equal to the equation of the original curve, which is just a times x minus p times x minus q times x minus r, right? So okay, so we notice we've got an x minus q both sides here, right? And I can cancel those because, you know, we're not looking for the solution where x equals q, right? So we're looking for other points. So let's just get rid of those. You could just factorize them if you preferred as well, I suppose. And I can also cancel the a's here, right? So I've just got q minus p times q minus r equals x minus p times x minus r. So we've got a quadratic in x here. So let's just try and tidy this up a bit. So I've got q squared minus r plus p times q. Let's just write it like that. Plus pr. Same on this side, I've got x squared minus p plus r times x plus, again, pr, so these prs cancel. So let's bring everything to the right hand side here. So I've got 0 equals x squared minus p plus r times x plus p plus r times q minus q squared. Okay. Now, so we can write this as x squared, because I've got this p plus r factor, right? So I can write that as x squared minus x minus q times p plus r minus q squared. And actually the x squared minus q squared, that's a difference of 2 squares, so I've got, you know, x minus q times x plus q minus x minus q times p plus r. So again, you know, I can factorize this x minus q, and I'm just left with x plus q minus p plus r. Okay, and again, we're actually not interested in this x minus q factor, because that just gives us x equals q again, and we're looking for other intersections apart from x equals q. So this is just 0 equals x plus q minus p plus r, right? So so now we showed that earlier if the tangents are parallel, then 2q equals p plus r. Okay, so let's just recall that here. 2q equals p plus r, right? But this is showing us that, you know, the final intersection here is at x equals p plus r minus q, right? Okay, so, you know, if the tangents are parallel, then you know, p plus r here is 2q. Right, so we get x equals 2q minus q equals q, and there are no other intersections. Right. On the other hand, you know, but if the tangents are not parallel, then we're going to obviously not get this condition that 2q equals p plus r. Then then this x equals p plus r minus q will give a distinct point of intersection. Okay, and that's all we wanted to show, that if the tangents are parallel, we just get this one point of intersection. If the tangents are not parallel, then we get some other point of intersection. So we've proved the if and only if statement there as well.